Greetings of the day. Welcome to the course on Operations Research Technique. We are right now in unit number 2, and unit number 2 comprises of two models. First one is assignment model and second one transportation model. If you remember, in earlier lectures we have finished with assignment models where the requirement was square matrix and we were assigning one facility to related only one facility, that is one-to-one assignment was the basic motto objective of assignment models. Now from today we'll start with transportation model, which is widely used in industries, and we know that in industrial scenario goods are produced in factories and end user is the customer, and there is transfer of goods from the factories to the end user, that is customer, through different mechanisms. In today's environment we are well conversant with the word supply chain, and supply chain management takes care of this aspect. Now when we talk from the point of view of customer is always interested in low cost product. At the same time he is interested in quality product. So two demands from the customer for any type of product: cost has to be low and it should be quality product. So when we are considering cost of product, one of the component of cost of product is transportation cost, that is cost involved in transporting the produced commodity in the factory to the end user. And if we want to reduce overall cost of the product, then the essential component, which is transportation cost, is to be focused, is to be given due attention, and here the objective function will definitely be then minimize transportation cost from customer point of view. This is one aspect. Suppose other aspect of transportation business, if I am running one transportation industry, I am having ply of trucks and I am commuting across India from one city to other city to transport goods of the customer. Now as an owner of the transport business, my intention will be definitely not to minimize my profit. It will be reverse. My intention in that case will be to maximize the profit. In earlier case what I have narrated, it is the basic objective when it comes to cost for the transportation is to minimize the cost. But if I am looking from the point of view of transport business, and if I am owner of that business, my sole intention will be to maximize the profit. So maximization profit will on other side will be only possible provided I apply some logic or means to reduce the cost of transportation. Once the cost is reduced, naturally the profit will be maximized. So everybody knows that goods are produced in the industry, and then those goods are supplied to the distributor. There are big warehouses across country. From warehouses, those are again distributed to distributor in the second chain, and then to the dealers in the particular city, and from dealers to variety of retailers, and from retailer the product goes to consumer. We know two modes. In the era of digitization, we order commodities through various apps like Amazon, Flipkart, wherein we directly get the component or goods delivered at our point of use. There are some commodities where as a customer I have to go to the shop, I have to bargain if possible, and then pick up the component and take it to the point of use, that is to your residence. Ultimately what we will be dealing in this model is goods transported from factories to the cities with possible modes, and our intention as a OR specialist, operations research specialist, will be to minimize the cost of transportation. So the sole objective of transportation model will be to minimize cost of transportation. Again, I will underline the statement, to minimize the cost of transportation. Now, in this particular slide, which is visible to you on the board, some aspects related to the transportation are given. I will explain those aspects. Now, we know this is the area where factory is written. So, goods are produced in factory and end user is customer, a person who is using that particular product. Suppose car is produced in the factory, suppose refrigerator is produced in the factory, air conditioner is produced in the factory, shoes are produced in the factory, or you take any name of the component product produced in the factory will go to the end user. End user is a person who is using that. And suppose we are interested at this entity, that this person is interested in, I am not touching all areas of this because this is related to performance aspect. My intention is to give you the flow path for how commodities are produced in the factory, transported to the warehouses, transported to the distributors, to the retailers and to the end users. So from factory it goes to warehouses. Big warehouses are there which are owned by some personalities. Then from warehouses it goes to retailers, and why there are so many means, you can say here so many means are given how that particular component is given or is dispatched. And then from this point, here again the customer is given, the customer can reroute the shipment if, but these chances in our country are very less. Customer don't have right to reroute the component. The component once we ordered will be delivered by the company through specified route only. And like this, if I want to summarize this sketch, it starts from factory, that is industry, then it goes to distributor, from distributor it goes to retailer, and ultimately you and me who are end user of that particular product which is being produced in the factory. So it travels like this, the same product. It never happens that the component produced in the factory directly reaches to the customer. It never happens. There is always a chain in between which takes care of shipment of those goods in proper manner to particular distributor or retailer, and from these to the customer. Now these persons have to take care that while reaching that particular component to the customer or product to the customer, the cost of transportation, whatever possible, is to be minimized. That aspect is to be kept in mind. So, as you can see now on this slide, this is the gist of the transportation problem. I will explain each and every term of this gist. The structure of the transportation problem involves large number of shipping routes from several supply centers to several demand centers. Suppose here the supply center, what is the meaning of the word supply center is where the products are being produced. It is origin. It is origin where commodities are available. Those are supply centers. Like a particular company, automobile company, it is not binding on the company that they are producing the cars in only one cities. The cars are produced maybe some at Chennai, some at Gurgaon, some at Hisar, some at Delhi, and those are to be transported in different cities like say Bombay, Calcutta, Nagpur, Bangalore, or the city you name where it is required. So from Gurgaon to reach to Chennai, one demand is from Chennai, other demand is suppose from Bangalore, third demand is say from Bangalore. You have to select which particular route for different available factories to different requirement cities you will suggest in such a way that the cost of transportation is minimum. So shipping routes are available from several supply centers. Again here I will write that supply centers are nothing but these are origins, and demand centers are nothing but where it will be needed. So in the language of engineering these are called as destination. So ultimately it is a matter between source of origin to the required locations which we call as destination. So origin will act as a supply, means here it is from, destinations will be needing, so we will write to. So basically the structure of transportation problem will be from origins to destinations. Origins are supply centers, destinations are demand centers. I will explain again these in detail with numerical. The objective is to determine, now see the theme, the objective is to determine the number of units of item. This is very important. Number of units of items or other name commodity or product that should be shipped from, say here the word origin which I have mentioned here, from an origin to destination. Here I have mentioned it is from to business. Number of units of an item which is referred as commodity or product from origin to destination. From origin to destination. How? That is very important. In order to satisfy the required quantity of goods or services, to satisfy the required quantity of goods or services at destination. So one thing you have to keep in mind while doing all this business, our most important criteria will be the cost of doing this business, that is cost of transportation. Cost of transportation has to be in any case minimum. So this will be the only objective function if it is cost. If it is profit, objective function will be maximize profit. Now one thing again what we have to keep in mind is, as we have discussed these words origins and destination, origin and destination. So origin will always supply and destination will always demand. So students, in transportation model you will frequently come across the two important words, supply and demand. Supply will be from origins, demand will be from destinations. Origins means factories. Factories will supply. Destinations means cities, places where that will be required. So it is the business of supply and demand. Here you can see the important highlighted word, satisfy the required quantity. Satisfy the required quantity means whatever is demand from that particular destination, you have to make that demand to be in the form to be satisfied. So supply centers will supply commodities and demand centers will get those commodities as per their wish, as per their order. But as a OR consultant, as a OR specialist, your task will be to minimize the cost of transportation from related origin supply center to related destination or demand center. I think this is clear. If the concept is clear, we'll go ahead. Now, we have seen in unit number 1 that linear program and how we are formulated. We also studied to formulation of linear programming from the given constraint. In the similar fashion, for transportation problem, we can write equivalent linear program. Before that, we have to get through these terminologies. Again, I will reiterate the things what we have discussed in previous slide is origin will supply. Then we have studied one word, destination. So definitely this destination will demand. Now we'll see these variables. The objective, as I have stressed, in transportation problem, the objective will be to minimize transportation cost or if it is maximize profit. So students, you have to keep one thing in mind. The objective function for transportation model can be in two categories. One is cost, if it is cost related, minimum cost if it is profit related, maximum profit. Now let AI, now again one thing, I will stands for, that is common mathematical concept, rows, and J's will be for columns. I will stand for rows and J's will stand for column. Let me draw a simple matrix. Suppose I draw here 3 by 3 matrix, and here I write from to, suppose. So from is related to origin, to is related to destination, and what are the contents of this inside cell that we will go through in detail in further slides. Let AI is the quantity of product available at origin I. So this from means it is acting as origin. This is nothing but origin. Now I1, I rows. So this is I1, second I2, third row I3. Quantity of product available at origin I. So that available, I will be writing over here, available. Suppose I write 20, means at one location total availability is, let me give it like that, 1, 2, 3. Or let me draw a bigger matrix. I will draw that bigger matrix over here to understand the concept. Suppose the things are like this. These are the requirement centers, say destinations, labeled as ABC. I can write it as 2. This is from, suppose the variables are JKL. So from, which act as a origin, will always supply, and demand will be from destinations. So here we will be having demand values. I want to explain this term. Let AI is the quantity of product available at origin I ranging from here, for this case I1 is J row, I2 is K row, I3 is L row. Similarly, J1 is A column, J2 is B column. I have written there, J represents column, I represents row. So J3 is C column. Now here suppose I write 20, 15, 10 like this. So the meaning is from J maximum supply is 20 units. So that is given quantity of product available at origin I. So at J maximum availability is 20 units. At K maximum availability is 15 units. At L maximum availability is 10 units. That is the meaning of this particular AI. BJ quantity of product required, demand. Suppose arbitrarily I write 18. And here suppose we write 12, 8 like that. Means maximum requirement from city A is 18 units, maximum requirement from city B is 12 units, and maximum required from city C is 8 units. These are the supply and demand for this particular case. Suppose a hypothetical case which we are taking for understanding purpose. quantity of product required at destination J. To explain this concept through this is CTA. CTA needs 18 units of product. CTB needs 12 units of product. CTC needs 8 units of product. That is the meaning of BJ. Cij is the cost of transportation of 1 unit from source I to destination J. Now students, the story is like, suppose I am writing like this and I am writing some values in between. Suppose these are arbitrary values we have selected to understand the concept of, suppose I want to explain Cij. Ij from I to J. If I focus my attention on these two value, what is written in K A cell, the meaning of this is to transport 1 unit of product from K factory or K city to A city is rupees 2, if it is in units of rupees 2. For 9, I will explain it as for transporting 1 unit of product from source or from CTL to CTC needs 9 rupees, if it is in units of rupees. That is the meaning how to interpret Cij. Now we will see Xij. The quantity transported from source to destination. Now this thing will be given to us. Suppose the solution obtained is like this. Arbitrarily I am again telling. Suppose the solution obtained is like this, 10, I am only writing two values, 12, 5 and 5. Suppose, so this 10, this 5 and this 5 represents Xij quantity. The units, the quantity transported from source I to destination J. Suppose my allocation is like this, means 5 units are transferred from J to B. For this 10 value, I will interpret as 10 units are transferred from J to A. Got it? And now, what will be the cost of transportation? If this is the per unit cost and if these are the number of units to be transported. So simple mathematical logic, cost per unit multiplied by number of units to be transported will give transportation cost. So ultimately it will be multiplication of cost and quantity. Now you can see here one very important aspect. Assuming all summation I ranging from 1 to m, ai is equal to summation j ranging from 1 to n bj. This is called as very important Riemann condition for transportation problem. This is called as Riemann condition for transportation problem. That is, before you start to attempt, again I am saying, before you start to attempt finding solution of the transportation problem, you must satisfy this condition, which is reflected as this that is total supply is equal to total demand. Total supply is equal to total demand has to be solved. If it is not, make it by taking dummy supply or dummy column, and then only you can proceed. Once you know all these things, for this data you can write its equivalent linear program which we have studied under unit 1, and the linear program goes like that. For objective function minimize cost referred as Z, cost of transportation will be product of cost per unit into number of units transferred. This is for one station, like number of stations in the problem. So to add that you have to use summation, double summation, because one stands for rows, one stands for column. Rows goes like i's, column goes like j's. So I raised to m, j raised to 1. Now if you recall our discussion in assignment matrix, there we have specifically mentioned the size of matrix for assignment models has to be square matrix before we start finding solution or before we start optimizing the problem. There was a need that size of matrix should be n by n for assignment. This was very much needed. But now for transportation this is not required. It can be n by n or it can be m by n. Both square and non-square matrix suffice the need. But while going for this square or non-square, important condition is, again I am focusing my attention on this, when you start finding solution to the transportation problem, at very first step ensure that total supply is equal to total demand, which is the need. So this is the objective function, and we can write the number of equation in the form of linear equation. I will rub all this now. This is being explained. This was explained to you. So our attention will be now only on what will be the equivalent linear program. So equivalent linear program goes like this. Minimize total cost, can be a reverse, maximize total profit, double summation Cij Xij subjected to Xij equal to Ai, means these equations will be for all supply, and this equation will be for all demands. Suppose you are having 3 by 3 transportation matrix with supply equal to demand, you will have 3 equations for this rows, 3 equations for these columns, and we have seen in linear programming this is very important. Can you guess what is this? Many times in linear programming I have mentioned, if you are not putting this in your program and if you are trying through computer will not process your program. Can you guess what is this? Yes, right, you are right. This is non-negativity condition. Non-negativity condition, that is all xij values greater than equal to 0. The meaning is you can transfer quantities greater than 0, or at all you will not transfer anything. If you are not transferring anything, xij will be 0. If you are transferring something, it will be greater than 0. But it is never possible that you are transferring -10, -5, -2 products from city to destination city, and therefore this non-negativity condition is very, very important. The non-negativity condition is very, very important. So for 3 by 3 matrix, I will get 3 equations for this, 3 equations for this, 6 equation plus 7. For 5 by 5 matrix with balance supply demand, I will get 5 equation for rows. Why I am saying 5 equation? A is quantity produced available at origin I, so it goes like row wise. So first row, if there are 5 rows, I equal to 1, I equal to 2, I equal to 3, I equal to 4, I equal to 5. So it will go like as per number of rows and columns in the problem. So this is equivalent linear program for the given transportation problem. Now let's go ahead. This is very important. Once we know the structure of the transportation problem, I have mentioned this under the category of some important points. The initial required condition for any transportation problem, before you proceed, you need to have this mandatorily. I am marking it with 3 stars. This is mandatory. Total supply must be equal to total demand. In earlier case, I have mentioned this as Riem condition for any transportation problem. Unless and until we achieve this condition, we cannot proceed to find solution of the problem. Such problem is called as balanced transportation problem. Such problem is called as balanced transportation problem. In a problem where supply is not equal to demand, here I have used this sign, supply is not equal to demand, it is called as unbalanced transportation problem. But remember, you have to make sure that before you solve such problem, you have to go to this step of supply equal to demand. You have to be very perfect that total supply is equal to total demand. So we have seen 2 cases. One is when supply is equal to demand, which is the requirement of any transportation problem. It is referred as balanced transportation problem. When supply is not equal to demand, it is referred as unbalanced transportation problem. But anyhow, we have to convert that unbalanced transportation problem into balanced problem to satisfy the Riem condition. Now you may come across with this situation. Any cell I will explain what is the meaning of the cell in the matrix. Any cell with, this is not negative, this is dash. Any cell with symbol like dash, or we know this is infinity. The meaning, if that particular cell in the transportation matrix having dash or infinity, it is to be taken as prohibited transportation, meaning no transportation is possible on that particular route. I will explain this through example. Suppose again this is from, this is to, from A, B, C cities to J, K, L, M cities. Suppose this is the structure given, and suppose with various values of transportation cost given, arbitrarily again I am taking suppose the matrix is like this. Now here we can see two cells with infinity sign. One is this cell, other is this cell. The meaning is there is no possibility of any shipment or transport from city B to city J, or if it exists at this place, there is no chances of any transportation. Transportation is never possible from A to L. Looking to the cost parameter, so infinity is, you won't get assignment in this particular cell, or in other way, this infinity, suppose there is no infinity, suppose you replace this by this, like for 3 by 3 again we can take 7-4 3 2 8 9 6 7, means again if we write from A, B, C to D, E, F, and if this cell is having dash, means this dash is nothing but this dash, which means prohibited transportation. That is there is no possibility of transporting commodities from A to E. There is no possibility of transporting commodities from A to E. That is not possible. Got it? This is what is preliminary requirement for proceeding for finding solution to the transportation problem. I have written one thing over here. Assignment problem is complete degenerate form of transportation problem. So if you recall our discussion in earlier slides, we have clearly distinguished between transportation problem and assignment problem. Advanced step, as there is an assignment problem, is complete degenerate form of Now I will explain this concept when I will be switching over to directly finding solution to the assignment problem, this transportation problem, and how it differs from conventional assignment problem. Now this particular structure I have explained prior to this. So through this let us try to understand. So this from which I have written here is written here from, this 2 is written here 2. So row wise it is from, column wise it is destination, and then we can find some values of C11, C12 in this particular matrix. So right now we'll stop at this particular point, and in next lecture I will start my teaching from this slide with important aspect of finding initial solution to the transportation problem and then how to optimize it. So right now we'll stop at this point, and from next lecture I will continue with further part of the problem.